All right, hello everyone. So we have a linear algebra question. Is the vector 1 minus 1, 4, reading down as a column, in the span of the set 1, 0, 1, 2, 1, 2, 0, 5, 5? Okay. So what do we mean by that? What do we mean by saying is a vector in the span of a collection of vectors or a set? So what we're asking is, do there exist constants C1, C2, and C3, all real numbers, such that C1 times the first vector 1, 0, 1 plus C2 times the second vector 2, 1, 2 plus C3 times the third vector 0, 5, 5 equals 1, negative 1, 4. So what you're always asking when something's in the span of something, you're always saying, is there a way that I can rewrite the vector and as a combination, linear combination to be more specific, of the vectors in that set, in that span? Okay, that's what we're saying. So that's the question, and then this is how it's phrased mathematically here. Let's put that in red. And yeah, well, if that were the case, then I could go ahead and, based on what I have, I can do some algebra here. So for example, that C1, C2, and C3 can be distributed into each of these column vectors, as we like to call them when you have one column. And you would have C1 times 1 is C1, 0 times C1 is 0, and then C1 times 1 is C1, C2 times 2 is 2C2, C2 times 1 is C2, and then C2 times 2, again, is 2C2, and 0 times C3 is 0, C3 times 5 is 5C3, C3 times 5 is 5C3, okay? So distributing that, and because these vectors in themselves are matrices, I can add up the components, and you would make one matrix right here whose first row would be C1 plus 2C2 plus 0. So I'm adding these first components. And then the next row would be C2 plus 5C3. And then the last row would be C1 plus 2C2 plus 5C3. Okay? So likewise, just like I did with that first row. And all of that is set equal to 1, negative 1, 4. Well, if you have two matrices that equal each other, as it is the case here, then each of the corresponding components have to equal each other. So the first row has to equal each other, the second row has to equal, and the third row has to equal each other for both. So you come up with a system of equations right here. Now, the next step is, there's a variation on how to do this, okay, in terms of how to find the values of C1, C2, C3. One thing I could certainly do is I could go ahead and set up a matrix, and like I did here, and try to find those constants by using Gaussian elimination, okay? And if I do that, you would get something like this. This is reduced row echelon form. You don't need to do all that. You just, I just wanted to keep it as simple as possible. So from here, after you take this matrix and row reduce, you get this, and this implies that you have a solution, and that's what we're looking for, that you have a solution. So C1 is 9, C2 is minus 4, C3 is 3/5. Now, we're not necessarily interested in the actual solution, just that there is a solution. So let me expand on that a bit. So yes, it is in the span, but when we get to this point right here, with the system of equations, instead of me I could have done this in terms of a matrix multiplication. So for example, 1, 0, 1, 2, 1, 2, 0, 5, 5, then C1, C2, C3 equals 1, minus 1, 4. And what I could have done is see if this matrix right here is invertible, and if it was, then there would be a solution. It'd be a unique solution. And how do I show the inverse exists? Well, you can take a determinant, Okay, that's one thing. So I don't know if you've covered that in class or not. I specifically went to the row reduction because a lot of people haven't covered that yet in class, but you can do that by taking the determinant. And if the determinant does not equal 0, there exists a solution to this, and it's unique, okay? So that's one of the equivalences that we have about systems of equations, right, if we can reduce the identity, it's the same thing as saying that the inverse exists, which is the same thing as saying the determinant doesn't equal 0. So all of those three conditions are equivalent, and it shows that there's a unique solution. So yeah, so at this point, there's various ways of doing it. Again, I just picked row reduction. A lot of people will ask me, hey, is there a way I can reduce all the work here? Technically, by definition, this is what we mean by the span. Now, what you could do is you could certainly jump to what I have here in the black circle, the system of equations here. So, and if you look at each of the columns representing the coefficients of C1, C2, and C3, they are the same as the vectors. They're multiples of the vectors 1, 0, 1, 2, 1, 2, and 0, 5, 5. Okay, those are the ones that we started out with. Okay, so what I'm trying to get at is that you can kind of just put these directly into a system of equations, or one big matrix with those as columns, and go from there. So that's a shortcut. I personally don't like doing that because I often make mistakes when I do that. So I'd rather just write this out like I did when I showed this for the first time. It's just a little easier for me. Okay, so once again, just to reiterate, that's what going over what we did. We talked about what it means for a matrix, or sorry, a vector to be in the span of 3 other vectors, or 4 or 5, whatever. And all that means is that we can write it as a linear combination. The vector in question can be written as a combination of the vectors in the set of the span. And the linear combination is just when you multiply each vector by a constant, add them up, and you try to see if they equal, there's some constant that equal the vector in play, and we set up a system of equations, okay? And that was it. So because it existed, there it is in the span. So we would say 1 minus 1, 4 is in the span of the 3 vectors that we had written earlier, okay? All right, well, thank you for your time. Hope this helped.